This is video 8.4. We're going to be looking at something called potential energy curves. What that is a graph of potential energy versus position. So, draw an example here. This is the energy associated with a particular force. Let's say that it happens to look like that. And it basically tells you the potential energy associated with a particular force when a particle is at different locations. And there's a lot of things we can learn about this. These graphs are one of the main tools that physicists use when we're looking at atoms and so on. Now, the first thing we know is that potential energy, the change in potential energy, is equal to negative W, and the work is equal to the force times the displacement. So what we've got here is delta U equals negative F delta X, which, if you divide both sides by delta X and turn it into a derivative, means that the force is the negative of the derivative of this graph. And derivative just means slope. So if you look at this point right here, the slope is negative, and that means the force is positive, which means at that point, the force on the particle is pushing it to larger x. Or another way of thinking about it, the particle wants to go downhill. So here the force is downhill. Here the force is downhill, but that means the opposite direction. Right about here, the force is equal to 0 because the slope is 0. And there's a lot of things you can figure out from this. One of them is the concept of a turning point. Let's say that we have a particle, and when it is at this location here, its kinetic energy is equal to 2 joules, and I'll put a scale here. So right there, the kinetic energy is 2 joules. The potential energy at this point is negative 4 joules, and so the total energy is negative 4 plus 2 is negative 2 joules. That means if we look at the total energy for this particle, it's right there. And that means that this particle can never get higher than this point, than this level. And so it's going to oscillate back and forth in that well there. And we call these points here turning points. Which is the subject of the next slide. Oh, there we go. Well, we kind of already did that. You should know what a turning point is, given a value of kinetic energy at a particular point, be able to calculate the total energy. That's what this number is. And then the turning points are places where the potential energy is equal to the total energy. In other words, kinetic energy is equal to 0. Now there's another concept called equilibrium points. And remember, equilibrium was a term we had that indicated the net force was 0. And so we're going to continue using that. And that means the potential energy has 0 slope at these points. And so we go back and we identify equilibrium points with orange. Here's an equilibrium point. Here's another equilibrium point, another one, and one more here. Notice that those are all minima or maxima on the graph. And there's a couple different kinds of equilibrium. The first kind is neutral equilibrium, and that occurs when if you displace the particle from equilibrium a little bit, it will still be in equilibrium. Basically, that's where it's flat for a large distance. This is a neutral equilibrium point. The other kind of equilibrium are stable and unstable. Stable equilibrium means that moving the particle a little bit to one way, a little bit to the side, will make it come back. And so if we look at this particular equilibrium point here, if we move the particle back there, it's going to tend to roll back to the low point. So these low points, these minima, are stable equilibrium. And then unstable means that if you displace the particle a little bit, it's going to keep going farther. And that corresponds to a maximum. So recap, neutral equilibrium, the graph is flat. Stable equilibrium, graph is a local minimum. Unstable equilibrium, the graph is a local maximum. You should be able to look at one of these graphs of potential energy and tell, okay, where are the equilibrium points? For a particle with a given total energy, where are the turning points? And then describe qualitatively the motion of the particle as it moves under the influence of this force. For tomorrow, I'm going to be checking question 6. You should be able to do most of the chapter 8 problems at this point.